This time, we are asked to prove the probability of some variable x given another variable z can be written as the summation over the instances over the values of a variable y, some other variable, which is a summation of probability of x given y and z times the probability of y given z, which then we have to prove is equal to the probability of x given w, y, and z times the probability of w given y and z times the probability of y given z, all summed over y and w, which implicitly means is a double summation. So summing over y's and summing over w's, each independently of the other. We will start with the left hand side, of course, because it looks much easier than starting from the right, and see how far we get. First, let's demarginalize. As a quick reminder, what we mean by a marginal: probability of a, some random variable a, can be expressed as a sum of joint distributions, probability of a comma b, where b is varying over all its possible values, so iterating through every possible value b can take. Do note that b is assumed to be discrete here, which is why we have the summation and not some kind of integral. Okay, so let's demarginalize the left hand side with respect to y, because we can see we want to actually have a summation over y, and that will kind of bring our expression into what looks like what we need to prove. And voila, that's what we've done. We're not quite done yet, so we now can employ the fact that we know the definition of a joint distribution using the conditional, because we know a probability of a given b is the probability of a and b over the probability of b. Rearranging that, we just get the probability of a and b is equal to the probability of a given b times the probability of b. And applying that simply to the expression inside summation, we get exactly what we wanted to prove. Okay, now onto the second half of the proof. We need to start with where we've got to so far and apply the same old tricks we've been using so far. So first, we're going to look at this bit inside the summation and say, why don't we demarginalize this with respect to w? Because we can see that we want a summation over w in our final answer. And doing that, we get this, where our demarginalized form is this entire summation, replacing the probability of x given y and z. Next, what we need to do is use the same trick we'd known before, the definition of a joint distribution. But in this case, it's going to be the probability of x and w given y and z, which we are replacing. So we're letting the x be the a's and the b's be the w's. And that gives us this expression. So we've simply replaced that joint distribution with a conditional times a single. And now it's just a matter of moving the summation signs and rearranging the terms, and we have this expression. This is actually equivalent to a final answer, but just so it looks the same, I will write it in the same format, because the notation here used is y comma w as the indices of the summation, just to make it look, I guess, shorthand notation for what's actually happening, which is the double summation. And that was that. Not too difficult to prove, and we've got the answer.